Example 15.4 wants us to define a polynomial function called h. And the requirements on h is that it needs to be of least degree. H of 2 needs to be negative 636, and we're supposed to have zeros of 6 and negative 5 plus 2i. So because I don't have the degree, it makes it a little difficult to immediately apply the linear factorization theorem. Let's start with the zeros. Let's let C1 be equal to 6, and then C2 be equal to negative 5 plus 2i. Now, if we look at just these two zeros, you would think that the implication is you're going to have a degree of 2. But the problem with that is that one of these is a complex zero. 6 is rational, but negative 5 plus 2i is complex. And we have a theorem called that conjugate pair theorem, and it says that if I have one complex zero, I must have a second complex zero. So this actually implies that there is a C3 of negative 5 minus 2i. Now that would lead me to believe that I should have a degree 3 polynomial. Then we would say h of x is equal to a times x minus 6 times x minus negative 5 plus 2i times x minus negative 5 minus 2i. And I'll clean that up just a little bit. A times x minus 6 times x plus 5 minus 2i times x plus 5 plus 2i. Now let's go back and look at the requirements. We used both of the zeros, 6 and negative 5 plus 2i, and because one of them was complex, we added a third zero, and we didn't need to add any extra multiplicities to this, so that way it guarantees that this would be the least degree possible. We use the name h by calling it h of x. The only thing we haven't used yet is h of 2 equals negative 636. This is going to help us to be able to figure out the value for a. But we're not quite ready for that yet. I would like to go ahead and put my polynomial function into a standard form. Now the factored form, which is given to us by this linear factorization theorem, has two complex factors and one real factor. And I would really like to get rid of the complex factors. To do that, we're going to need to do some distribution. X will multiply with x plus 5 plus 2i. 5 will also multiply with x plus 5 plus 2i, and negative 2i is also going to multiply with x plus 5 plus 2i, giving us a grand total of 9 distributions. Let's set this up. H of x is going to equal a times x minus 6 times x squared plus 5x plus 2xi plus another 5x plus 25 plus 10i minus 2xi minus 10i minus 4i squared. Now on that last distribution with negative 2i and positive 2i, certainly negative 2 times positive 2 is where we get the negative 4, but then I times I, you can treat that like it's a variable. So if I said x times x, you would get x squared. I times I gives us I squared. That's where that comes from. A lot of distribution. It looks ugly, but there's great things that happen. 2xi minus 2xi, gone. 10i minus 10i, gone. Plus 5x, like terms. Let's go ahead and clean it up. A times x minus 6 times x squared plus 10x plus 25 minus 4i squared. When we first talked about complex numbers in our polynomial discussion, we had talked about two things. Number one was that the square root of -1 would be equal to I. And we've used that particular definition several times throughout the polynomial sections. But I also gave you that I squared would be equal to -1. And we didn't use it after I stated that. But today we're going to need to. I want to focus on that minus 4i squared for a moment. And when I isolate minus 4i squared, I need to think of it as negative 4i squared. And if I do that, then I can think of this as -4 times -1 by replacing I squared with its equivalent -1 representation. And then -4 times -1 just gives me +4. So what this really means is that this polynomial isn't going to have any i's in it at all once we finish that multiplication. This is going to be x squared plus 10x plus 25 plus 4, in which case we get another pair of like terms. Combine the two constants together, and we have h of x equals a times x minus 6 times x squared plus 10x plus 29. And then I want to continue with the distribution process, trying to get this further into the standard form, because it's still in a factored form, just not a linear factorization. And I'll take x and multiply it with x squared plus 10x plus 29, and also do the same thing with -6. Once you multiply, you will then combine like terms, and I have the result of that here. This will be a times x cubed plus 4x squared minus 31x minus 174. With the exception of the value for a, we have completely gone through all of the other requirements, all the other circumstances or conditions, if you will, for the function. But we haven't used the fact that h of 2 has to be -636. Let's test it out. Let's test out our equation by simply plugging in 2. Plug in 2 for all the x's, and then this is going to tell me that h of 2 is going to be equal to a times -212. My hope was that when I plugged in 2, I was going to get -636, but clearly I didn't. I was getting -212. But I can use a as a means to fix that. A is going to be a multiplier to force the answer to be -636. So let me show this algebraically. If you can see it, then you can just tell me what a has to be. Let h of 2 be equal to -636. And then we're going to get the statement -636 is equal to -212 times a. And then when you divide both sides by -212, you're going to get 3 is equal to a. That means we have the last piece to the puzzle. Go back to writing h of x. Now you input 3 for a, and you'll have 3 times x cubed plus 4x squared minus 31x minus 174. And since we've already come this far, we might as well go ahead and finish the job of getting it completely in standard form, because it is still technically in a factored form because we have a 3 out there in front as like a GCF type factoring. So now we would say h of x is 3x cubed plus 12x squared minus 93x minus 522. And we'll make our function definition h colon r to r given by h of x is equal to 3x cubed plus 12x squared minus 93x minus 522, giving us the function definition for h that has h of 2 being equal to negative 636, 6 and negative 5 plus 2i are zeros, and it is the least degree that we could possibly make because we had to have a third zero of negative 5 minus 2i.